Okay, after a while, a video in English language. Today I want to show you the bug fixing of Redis vector sets from the point of view of Endianness, safety. You know what little endian and big endian are? So different computers have a different way to represent numbers. For example, the number 1 in a 32-bit integer in little endian will be represented by the bytes 1000, which is the least significant byte is on the left. In big-endian it will be 00000001. So it's like big-endian, it's like the order you would write the number with pencil and paper, basically with the most significant digits on the left. But actually, little endian is at this point the standard. There was some time in the 90s where you could have computers in little endian, like Intel-based computers, and computers using big-endian, for example, Solaris workstations and others. But now, slowly, everybody converged to little endian, and AMD 64 is little endian, Intel is little endian, the Raspberry Pi, and there are. I believe that the ARM platform could be used in both ways, but basically everything is little endian. So this bug fixing here will have very little practical sense, but it's important to write correct code. But first of all, I want to show you something. Endian.c. Basically, you can very easily test if a system is little or big endian in this way. So you create an integer and put 1 inside. Then you create a char pointer that is at the address where this integer is stored, and is we print print pd0, pd1, pd2 and p of 3 of my array. If I compile this program, I will see that the first one is 1, because we saw this here. So basically, if I want to check if something is or not little endian, is little endian, I write this function p d0 not equal to 0. So is computer little endian is little endian? Yes, otherwise no. Let's compile this program. Is this computer little endian? Yes. So it's very simple to test at runtime if your computer is or not a little endian. However, now I want to show you something different and more convoluted. So I have a serialization function here. In vector sets, because I need to serialize my HNSW nodes into disk for Redis storage, but this function is generic, is not specific for Redis. Basically, all my HNSW nodes are in a linked list, and I can just navigate one after the other and call HNSW serialize node function that will return this structure here. This structure here is HNSW ser node. It's a pointer to a vector saying me how many bytes I have for my vector, because HNSW, my library supports different quantization types, binary quantization, int8 quantization, so it depends on the number of elements of my vector and the quantization type. But the receiver of this structure basically will know that basically you call this function, you receive this stuff here, which is allocated here. This is not a good choice. You know, this function should take a reference to HNSW serialization node. It's completely useless that we continue to allocate. Oh, because anyway I allocated the copy of okay, everything so is allocated, so yes, it makes sense. So you get this, and then you get a number of parameters that are the node's edges, so the links, its neighbors, and all the other information. However, in order to simplify the interface to the programmer using this stuff here, I wanted to serialize everything as in 64-bit unsigned integers, parameters, whatever they are, and what number they are. So who calls this serialization function will have to save on disk or to transfer in the net or whatever we want to do with the serialized node. Just a blob, a binary blob, which is the vector, and a number of integers, of 64 unsigned integers. However, doing that required a way to store in these integers also floating point numbers. And I want to show you something about that. So imagine this to be instead 32-bit integers. So I have a float f, which has some value, and then I have this integer s, which is the serialization of my float. So to start, I want an assertion here that size of the f is equal to size of the s, okay? But they are the same because a float is single precision floating precision number everywhere, but the assertion could be useful. Then you can just memcopy inside your integer your float. At this point you can serialize this on disk in every way that will just be Endian safe, but just for the sake of simplicity, imagine that we have a buffer here of some kind, and we do sn printf unsigned. So we create basically the string representation of s, and then we open a file the file pointer it's at the end. Okay, then in a big, imagine that I saving this in a little Endian. architecture. And then I load it in a big-endian. Assume that I loaded back the buffer with the string representation and that I converted it back to a number in S. Then I do memcopy fs, so I copy into my float my serialized my serialization in a numerical form. And here you could ask yourself, will f will be the same? 1.23. Well, what is very interesting is that it will actually be still correct, because when I load the number in the big-endian representation, it will be reversed. So if the number was 1, for example, it will be, the bytes will be reversed. But also the float itself follows the Endianness, so it's also reversed. So it will be the same. So far this is Endian safe. Now the problem is that big-endian architectures are so scarce that I was not able to verify this in practice. To be honest, probably I should try with QEMU and some old Linux distribution, but it's so complex right now to access a big-endian, so this bug is so actually virtual that it's so let's resort to AI to see why this should work and why I believe I did an error in another part. So actually, to start, I want to show you the error that I did. So if I open the serialization function here, at some point you will see that here in this integer, one of the parameters that I use for the serialization, I do the error of serializing two float numbers into a single 64-bit number using a fixed offset that doesn't change with Endianness. So in the first part of this, in the first 32 bits, I store this float, L2, the L2 normalization, and in the second half, I store another float, the quants range. And I believe that at this point, I break this system, and I will find that my integers, after loading from little endian and loading in big-endian, will be swapped. To start, let's see if Gemini 2.5 Pro acknowledges that this system is correct. Please check carefully, making xdumps of examples intermediate steps if this is correct or not. This is something where I expect LLMs to hallucinate actually, but let's see if it is useful in this specific case. Yeah, it says that I am correct, and it's very nice that it splits its hexadecimal representation and then the binary representation. The memory layout will be indeed inverted in both the cases. Very cool. Then I will ask it. What about this? In this case, two floats are stored into a Uin64T. And let's see if it is able to spot the error. Because what should I do here is to check for Endianness of the system, and then check if it's the Endianness is big-endian, I should do this. So store the other in the other side, and so to swap the offsets. Unlike your previous program, no, this code is not portable, resulting will be, let's break the data, executing. As you can see, the final stored is completely different, implications and so forth. Now I want to, so basically the two floats will be swapped, but the right content. Let's see if it is able to verify this. Gemini, it's slow, but at least it hallucinates less, it's more powerful, it's a trade-off among things. Okay, yes, it acknowledged this. And then let's see the final thing. Int x equal 1 il test unsigned char lep unsigned char if il test if int is little endian equal lep 0 not equal 0, if is little endian go in this code path, else go in this code path. Does this fix the bug? I'm curious about the fact that it will understand that I need to do that also in the loading side of the code. Yes, this is a valid and clever way to fix the bug. This code will now produce the exact same uint6040 value, and regardless of the system endian, you have the problem independent of the solution that makes the data representation portable. Analysis of the fix. The goal is to create a canonical 64-bit number with one float consistently occupies the most significant 22 bits and the other. The code is a rule quants range. Okay, the Endianness check. This is a standard and correct C idiom to detect Endianness at runtime. Alternatives. Okay. Okay, that's interesting. This is a way to fix it without checking for Endianness. Your solution, for example, if worth noting, a common alternative that some programmers find more experience. This avoids complex reasoning about memory layouts. This version uses bitwise operation to define the layout, which is inherently portable. Okay, this makes sense. It creates two 34 numbers, and then it does like that. But in general, well, it's interesting that the fact that 2 times reversing still makes storing the number as a number, which is not what Redis does. It uses another system, but from our point of view, we know that the number we store is the number that will be loaded also in big-endian. And I will make sure that this is the case with QEMU finding an image. It's a nightmare now. Some time ago it was much simpler to find where I can find what's the simplest way to use a big-endian architecture. Compile code, test it. It's a shame that the compiler explorer does not allow you to execute the code. It's just cross-compiling and you see the assembly, but it's not possible to execute the code. In today's x86 and ARM dominated world, getting access to big-endian system can seem difficult. QEMU, yeah, the same. Yeah, I totally agree. Okay, now I'm going to write the actual fix. Bye.